So you just heard the introduction of Professor Brian Kolner from Conrad. I won't repeat, that would be a little boring. Just tell my personal story. Brian was a JILA visiting fellow, I think, in the early 90s, or at least you were visiting, yeah. And at the time, I was a Jan Hall's graduate student. And Brian, and I don't know how many of you, oftentimes we come from different perspectives. Sometimes, in order to teach electronics, you use a mechanical system, spring, to explain the LC tank circuit. Sometimes you use electronics to explain the mechanical system to certain students who actually are more comfortable with electronics. So it tells you sometimes you can have some intuition. I know how to align lenses and so on for spatial imaging, but I had no idea at the time, ultra-fast lasers, how do you do time domain propagation? And Brian, I think at the time, introduced this concept of time-space duality, where, of course, we can think of the perennial diffraction in space or dispersion relationship in the time domain are very strongly connected. And they can, whatever the intuition you have from the time domain or from the spatial domain, you can apply to the other and allow you to understand physics a little deeper. Today, he's going to tell us about taking that analogy further to quantum mechanics, even, talking about matter wave interferometry, where also there's a spatial aspect, but he's going to now think about time domain aspect to connect this and allow us to see whether there are new regimes can be reached using this kind of insight. Brian?
Thank you, June. Well, thank you all for coming. I'd also like to thank this wonderful institute, this glorious location, and marvelous intellectual horsepower. I'm just delighted and honored to be here. I really am. So I'm going to, as June said, talk about applying some of the usual ideas of space and time, that is to say, diffraction, Fresnel diffraction, and narrowband dispersion to the world of quantum mechanics. Now, I haven't done any experiments because I'm not sure this actually works. And I invite any of you with critical ideas and conjectures about why it might not, please come by the office or ask questions this afternoon that I probably can't answer. So it's going to be largely theoretical and mathematical, but thank you. But, oh, that is better. But fear not, the math is nothing beyond a Fourier transform of a complex Gaussian. So if you've seen one, you've seen them all. Okay, and if you look in Tony Sigmund's book, he has the expression there for such a transformation, and he calls it Sigmund's lemma. So I always rather adored that. Okay, so let us get started. Good. So I'm going to start off with my thesis, and just to tell you what we're going to talk about and what the pathway is. And it all hangs on the fact that the governing equations of paraxial diffraction, narrowband dispersion, and free particle wave propagation in the quantum world are all the same differential equation. They're complex, some people call them complex diffusion equations. They are in fact complex parabolic differential equations, and they're all of this particular form up here. And lenses in space and time domains combined with the propagation solutions for such an equation have enabled spatial and temporal imaging systems. We've known spatial imaging for many centuries, but only in the last 50 or so years have we known about temporal imaging. Now, suppose you can find the equivalent of lens action for matter waves. Then because of the similarity between the Schrödinger equation and the equations of paraxial diffraction or dispersion, you should be able to create an imaging system that would allow for, say, magnification, stretching, demagnification, compressing, local time reversal even, and other waveform manipulations that you can be familiar with from classical optics, and then apply that to quantum mechanical wave functions. Okay, so space lenses are what we know and love. They produce a transverse quadratic phase variation by refraction or reflection, diffraction, or even a spatial pinhole, plus the propagation solution. That gives you a spatial imaging system. Time lenses, as I've done a lot of work in this area, requires a longitudinal quadratic phase modulation. You can do this with an electro-optic phase modulator. You can do parametric mixing. We pioneered that in my group with chirped pump Or you can use a fast temporal shutter, which is the time domain of a pinhole aperture. And that's been demonstrated recently. That gives you temporal imaging systems. And then, as I said before, if you could find a quadratic space-time varying potential, you could create a matter wave lens in principle. It's sort of a time-varying Aharonov-Bohm effect plus the free space propagation, which is the solution to the Schrödinger equation, and maybe make an imaging system. Now, I just want to say parenthetically, this is not a true Aharonov-Bohm effect, because Aharonov and Bohm, as we'll see shortly, wrote this stunning paper in 1959 about the effective potentials on wave functions in the absence of fields. Okay, everything I'm going to talk about for potentially imaging has got fields in it. Why? They're time-varying potentials, and E is proportional to minus the partial derivative of A with respect to T. So you can't have time-varying potentials without fields. Nonetheless, I think there's a sneaky way around this. Now, I'm going to review just very briefly the business of Fresnel diffraction. Is that red and green stuff up there, Chief? Is that green?
You can drag it down as the share. I tried to drag it off screen, but it's not the share.
Oh.
You just kind of click and drag it and pull it down, but I can't find a place to hide it.
Oh, you can't park it anywhere?
I don't think so. If you like in the green part specifically, the ID, yeah, there you go.
Oh, there we go. Gone. Thank you.
There you go.
All right. So Fresnel diffraction, we start with an electric field of all coordinates in time, and then we restrict it to a monochromatic field. And then we separate out the fast spatial phase variation. That is to say, the wave number K0 comes out in front. And then you have an envelope then in front U. And if you plug that expression for E in terms of the pulled out fast phase variation back into the wave equation, and then invoke the paraxial approximation, which says that the curvature in the propagation direction is small compared to the spreading in the transverse direction, well, you get the paraxial wave equation, known to everybody who's studied optics. And there is our equation du jour. That is the complex diffusion equation, the parabolic complex differential equation. First derivative in the longitudinal direction, second derivative in the transverse direction. If you Fourier transform that and pull a couple of theorems out of your hat, you can express that solution for you in terms of an integral over an initial spectrum of wave numbers kx and ky at the initial plane z equals 0 times a term that's quadratic in the transverse wave number. So this is a quadratic phase. This is going to play a very important role in everything we talk about today. It's a quadratic phase filter. Okay, and then there's an inverse Fourier transform kernel here. So that's Fresnel diffraction in a nutshell. What about narrowband dispersion? Well, we start once again with a fully loaded electric field, and then we say let's limit this to infinite transverse plane waves. So we take out the transverse coordinates x and y, and we're only left with a z dependence. Okay. Now, we superpose a spectrum of these plane waves, okay? So E of z and t is now a superposition of plane waves where I've just moved the complex exponentials around a bit. And this is a spectral density function. That's the spectrum in frequency space, okay? That's all there is to it. Superposition integral. And now the key is to expand beta. Beta is the same as k. It depends on if you're an electrical engineer or a physicist, but they play the same role. They are the spatial phase shift per wavelength or per unit distance. And we expand beta to second order, which is reasonable for relatively narrow band spectra. That's what we do. And in the end, it makes it analytically tractable too. When you do that, when you expand beta to second order, plug it in here, and then do some variable substitutions, it pops out that E of z can be written in this form, which is carrier envelope form, okay? And related to that then is a differential equation for the envelope that is in this form, and it has in it the second derivative of beta with respect to omega, which came from here. It has also the group velocity, which is related to the first derivative of beta with respect to omega, and so forth and so on. That's not our equation du jour. But we can do a little trick. We can shift to traveling wave coordinates. I want to move with the pulse as it propagates in this dispersive medium. And if you do the correct coordinate, if you do the correct transformations of the derivatives up here, which is a good exercise for students, you have an equation, differential equation for the envelope A in the traveling wave coordinate system moving at the group velocity v sub g. Okay, so as time and space get advanced, you can stay on that wave packet and watch it go. Why is this important? Well, first of all, we've recreated the equation du jour, today's equation. But second of all, if you think of diffraction problems, you generally are talking about the way a beam spreads with respect to the x and y transverse axes when you're on axis. So if you think of it, the beam is confined to the axis. That's what paraxial means. Well, in the dispersion problem, before we did the traveling wave coordinate transformation, you've got a problem that's describing a wave packet that's propagating. You got to run to catch up with it. You do the traveling wave coordinate transformation, and now we have an equation that just sits there parked in the local coordinate tau. This is everywhere where this is 0 is the middle of your wave packet, and then you can think of psi as the evolution variable. As you crank up psi, you're effectively saying, where's the packet going in z? But I'm looking at it as it propagates rather than watching it move. You're moving with it. So that's an advantage. And envelope solution is once again found by straightforward Fourier transformation of the envelope equation and then solving that one-dimensional ordinary differential equation, superposition. And this is the spectrum of the initial wave packet A, okay, at the input plane psi equals 0. So that's a little bit of math. That completes the diffraction dispersion analogy, okay? And the key things are that beams spread in space about a stationary axis, the z-axis in this case, according to the paraxial wave equation. And in dispersion, pulses enter a dielectric and they spread out. And in the local time coordinate centered on the center of this wave packet here, the wave shape or the waveform A of tau satisfies a differential equation that's identical to the paraxial equation, okay? So now let's look at the three principal equations of the day. We have our paraxial diffraction, we have our narrowband dispersion. Let's add Mr. Schrödinger into the mix. So there's the free particle Schrödinger equation. First derivative in time, second derivative in space, and z is going to be our propagation direction. Now what I'm going to do is follow exactly the same steps as the previous two problems, but I'm going to show you every step in detail just for doubting Thomases and students who may not be familiar with this. It's really all the same stuff. So our equation of motion, we assume an elementary plane wave. And when you put that into the equation of motion, you get the dispersion relation. And you can go from differential equations, wave equations to dispersion relations, or back. If you know a dispersion relation, you can go back and reconstruct the wave equation. Then we're going to make a wave packet by superposition, just as we did in the other problems. And we identify the term psi naught of k as the initial spectrum in momentum space, if you like, because if you just grab these two terms together and consider this the momentum spectrum for some time t, if you let t equal to 0, evidently psi naught is the initial momentum spectrum, psi naught of k, and by the Fourier inversion theorem, that's obviously the forward Fourier transform of psi of z and t, which I've written over here. Okay, so just straightforward Fourier transforms. Next, we do the narrowband approximation about some mean wave number or momentum, if you like, k naught. You expand it to second order, okay? And then since we already know we have a prescription for the dispersion relation, we can differentiate that and pop them in, okay? So now we substitute that Taylor series expansion into our superposition integral, okay? So right now it looks like a mess, but we can actually defeat it by doing a simple variable substitution, which I did, but didn't show you the steps for in the dispersion problem. We let all these k minus k naught terms here be defined as k prime. And when you do that, what happens is there's an e to the I k naught z here that does not participate in the integration. So we'll pull that out in front and recognize this as a carrier wave. How about that? And then evidently, this has got to be the envelope of that. So now we have it, whoops, bumped forward here. Now we have the wave function written in carrier envelope form under the assumption of a relatively narrow band wave function. Standard stuff. Now, it's going to be useful, once again, to transform to traveling wave coordinates so we can move with this quantum mechanical wave function. So once again, we make a judicious choice of traveling wave coordinates, and that modifies our integral. Now, interpretation. What are we seeing here is we have a traveling wave carrier out in front. This is an envelope function, but it's not an envelope that's propagating. It's an envelope that's stationary in the center of the traveling wave reference frame because there's no linear term in k here. It's the linear term in k that gives you displacement by Fourier theory. You take a function f of t, for example, and you displace it by t naught, you Fourier transform it, there's an e to the minus I t naught omega in the Fourier transform. So it's linear in omega, but if we're talking about wave numbers, we've taken out the e to the I k to first order term here. This is stationary. And it's multiplied by, look at this, a backward propagating carrier. How did that come about? Well, it turns out that the phase velocity is related to the group velocity by exactly 1/2. So in the stationary wave packet picture, the carrier, I have to do it this way, the carrier is moving to the left, and your wave packet is stationary in the traveling wave system, but that just says that the phase velocity is actually half of what the group velocity is. So it's no mystery there. Okay, so we've got the solution now for the simplest Schrödinger equation solution, and no quantum mechanics involved here. Okay, no propagator. Propagators are all this, actually it's all the same stuff. So we've shown that the three equations are identical, and their three solutions are really identical. They're integrals over, go back, they're integrals over an initial spectrum times a quadratic phase factor and inverse Fourier transformed. Term quadratic in the frequency domain or wave number domain here, and that's common to all three problems. Okay, so now let me talk about lenses for a moment. Remember, borrowing a page from Joe Goodman's book on Fourier optics, we can write a lens phase transformation as e to the I phi s, where phi is the space lens function, which depends on the transverse coordinates. And it has a DC term, or a non-spatially varying term. That's just the center. That's the e to the I kz through the middle of the lens. And this gives you the quadratic real space dependence of the phase of a lens, okay? So now it's interesting, we have a function that's quadratic phase, but in real space, not Fourier space. That's an important distinction, okay? K naught is just the wave number of the optical field, and is obviously the index of refraction, and delta naught is the thickness. And of course, we have the focal length, which I give a subscript S because we're going to have three different focal lengths in the talk today: space, time, and matter. So this is the focal length of a conventional garden variety lens with radii of curvature R1 and R2. And if you play around with equating these two phases, you can actually write this as K naught up here divided by the second derivative of whatever phi is up here. This is a generalized focal length. So it doesn't matter about the physical properties. It's K naught divided by the second derivative of this phase function here. And I've chosen to write it just to be easy on myself, going in the radial direction, taking the derivative along x or y, and not worrying about the fact that it's a two-dimensional function. This will pop up again and again. What about time lenses? Time lenses work exactly the same way. Let us say we want to identify a phase function for a time lens that is quadratic in the real space coordinate. In this case, it's time, not omega, not frequency space. That's set aside for dispersion. Okay, and let's write this just like we did for the space lens as the carrier frequency times the square of the variable of interest divided by 2 times an expression we'll call the focal time. Tau is the local time, and just like we did for the space lens, you can show that the focal time, f sub t, is omega naught over the second derivative of phi, whatever phi may be. In this case, we don't have a piece of glass with curved surfaces to identify a focal length, right, like they do in the old days. But it's mathematically quite sound to write this as omega naught over the second derivative of phi, because you might have various different types of lens mechanisms, okay? So you might as well leave it general, okay? And the key point is that a lens is realized by any mechanism that produces a quadratic time phase modulation in the local frame of the propagating waveform. Okay, now you can look at other properties of space and time lenses. It's interesting sometimes to talk about instantaneous temporal frequency. And you'll notice that if you have a quadratic time phase and you differentiate at one time, you get a linear frequency sweep or a chirp, okay? A time lens produces a linear frequency sweep or a chirp. You can also talk about the rate of change of the chirp, and that is called the temporal chirp rate, okay? And you can then turn that around and solve it for the focal time, f sub t, in terms of the carrier frequency and its instantaneous, the derivative of its instantaneous frequency. You could do the same thing with spatial frequencies for lenses, for example. You can take the first derivative of the phase function in space and talk about the instantaneous wave number in the x direction, or the instantaneous wave number in the y direction, and then relate that back to the focal length in space. And you can also talk about a spatial chirp rate, where it's minus k naught over the first derivative of the instantaneous chirp. And you can plot these because these are both quadratic phase functions, their instantaneous frequency and instantaneous wave number are straight lines. And this is kind of interesting to study. It's interesting to note that the slope here, okay, d omega dt times the amount of, some amount of time, delta t, is going to give you a net bandwidth, delta omega. That's a very useful property. The same with spatial lenses, that if you have an aperture, delta x, and you multiply that by the slope, then you get the total spread in wave number space, in k space. Okay, what about f number? F number, interesting concept. It's always the ratio of the focal length to the aperture. And those of you who have done conventional photography in your lives are really familiar with the F numbers printed on the rings of camera lenses. And you pay attention to this. And if you've ever taught Fourier optics, you can prove that the resolution, spatial resolution of any imaging system depends on the F number. And it gets better with lower F numbers. Anyway, you play around with this a little bit, and you can see there's the product of the slope of kxi, the derivative, with delta x. Well, that's your total spread in wave number space. So this is a very cool expression for the F number. It's the center wave number divided by its width. It's the inverse of the fractional bandwidth. In other words, it's telling you how fast the waves are diverging in real space, okay? High angular frequency, high angular plane waves diverging off the axis means that you have a large delta K. And similarly in time, you have exactly the same expression, and the F number in time, regardless of how you're making a time lens, is always the center frequency divided by the bandwidth induced or imparted by that time lens. It's the inverse of the fractional bandwidth. In other words, if you put a CW wave or a very, very long pulse into a time lens, it has a very narrow spectrum before it gets to the lens. After it goes through that time lens, you quadratically modulate it. You've chirped it. What have you done to its spectrum? You've broadened the spectrum, okay? And delta omega, the natural width of that spectrum, is indicative of how strong of a lens it is. So these are generalized expressions for these things. You can put them all in a nice table, which I did years ago, and put them side by side, and the similarities are quite striking. And I've left out any mention of the space lenses radii of curvature, and I just left everything in terms of general general concepts, and therefore these expressions are all independent of a specific mechanism. Now I want to talk about how you calculate the induced profile of a time lens, because we're going to take that over to a space lens, or to a quantum mechanical matter wave lens shortly. There's several different ways you can induce a chirp on a traveling optical pulse, and the one I want to concentrate on is the middle one, where this is an electro-optic crystal formed, for example, with two electrodes, top and bottom, and it's a transmission line. And you connect one end of the transmission line to a sinusoid, and it propagates the sinusoid down the transmission line. It's electro-optic crystal, so places where you have high electric fields, both positive and negative, you have large changes in the index of refraction. So it's a traveling wave change in the index of refraction produced by this traveling RF field up here, okay? And we're going to be concentrating on co-propagating a pulse at a cusp, positive or negative in here, where it's locally quadratic, okay? Because it's hard to make purely quadratic electric voltages. Why? Because they go to infinity in both directions, so you can't do it. You can also do this with a Gaussian pulse. The analysis is considerably stickier, so I'm not going to do that. So the question is, yes, please.
In the previous slide, are you assuming the optical propagation, sorry. You know, the second panel B, are you assuming the optical propagation and the microwave propagation are phase matched?
That's the ideal condition. It's an excellent question. And in the analysis, I will leave them independent, and you'll see the effect of phase mismatch.
Okay.
It works out very well. It's an excellent question. Okay, so we want to calculate the total accumulated phase on a wave packet as it propagates through this transmission line modulator. And you get the normal omega t minus kz, which is without any index perturbation. Then you get an integral propagated in space-time of that delta n, that propagating change in the index of refraction. We're going to call that gamma, the net retardation. And in a traveling wave reference frame, which is what I always like to change to, this accumulated phi is a function of the center of the traveling wave system, and tau is written this way if you make the substitutions up there. And this is approximately equal to just omega tau minus the accumulated retardation. This term is almost always zero because it's dispersionless. That means that a wave packet incident on the modulator will, here's the incident wave field. It gets multiplied by essentially this is where all the action is, this accumulated gamma up here. And so you get an output waveform times, which we're about to solve for, times that harmonic time function, okay? So in general, gamma in the traveling wave system is nothing more than an integral of the delta n, the change in the index of refraction. So let's assume that the index of refraction is a traveling wave, right, which it is. So, and we're going to use subscripts for the modulating field. Theta is just an arbitrary offset so that you can align the wave packet anywhere on the sinusoid that you want. So it's just it's a free parameter in this, and I just kept it in there. If you evaluate this integral, and you plug in the delta n cosine up here, you get this lovely expression. I should have put a box around this. We're going to see this actually for the case of the free particles as well. The principal parts of it are that delta phi is the velocity mismatch that you asked about, June. It's the 1 over the group velocity of the wave packet over minus 1 over the phase velocity of the microwave with some terms out in front, okay? And it's a sinc function, which means that it only gets worse as you get velocity walk off away from 0. When you get perfect phase matching, this term goes to 0 and the sinc function is unity. So the induced retardation is maximized when the velocity mismatch is 0. And we can grab all of the terms out in front and call this the peak phase retardation. And it depends on, interestingly, the propagation distance that you go, the peak amount of index variation that there is, that makes sense, the carrier frequency, and that's because the peak retardation depends in a sense on the curvature that you've got up there, just like in a real space lens, okay? The more of that lens bulges out, the stronger the curvature. That's sort of equivalent to having your carrier frequency out in front here, okay? So that's what you get for the accumulated net retardation. And here's some plots of gamma normalized to the peak gamma, overlaid with some mythical Gaussian pulse here just to see the basic relations. So this is in the local time frame, omega m tau. And if you have some walk off, the effect is it shifts the peak and hence the center of the quadratic phase part here off that Gaussian, either direction depending on whether the walk off is positive or negative. But if you're perfectly phase matched, you get the maximum amount of retardation. And in the traveling wave reference frame, the quadratic phase is right spot on. So here's the temporal imaging system compared to a regular spatial imaging system. In space, you analyze this stuff first in the Fourier domain. That takes care of diffraction from the object to the lens. So that's a quadratic phase in Fourier space. You multiply it by the lens transfer function, which is quadratic in the real space variables. Then you inverse or you Fourier transform back to wave number space, and you multiply this by, again, by a quadratic phase filter that depends on the distances involved here. And then you can show that there's a magnification m, which is minus the ratio of the output to the image distances or input distances and so forth. Temporal imaging is exactly the same way. We have our electro-optic time lens. I goofed up and I didn't draw this as a sinusoid, but nonetheless, suppose it's just a propagating quadratic phase in the middle here. For those of you who are old enough to remember diffraction gradient pulse compressors, I drew the input dispersion as a pair of diffraction gradients because this is a lovely way to make pretty good dispersion that's controllable. So you analyze the input dispersion in the frequency domain. It's quadratic in the frequency. Fourier transform you and multiply it by the quadratic phase in the real space, tau, inverse Fourier transform, and multiply it by the quadratic phase filtering in the frequency domain. And what you can show, of course, is that because the magnification has a minus sign out in front of it, if you have a wave packet that's an optical bit sequence of 1011, it'll come out magnified, stretched, preserving the profile of the bit sequence, but it'll be time reversed. And when I used to give talks on this, there's invariably somebody at the end of the talk would say, doesn't that violate causality? No, it's just, there's no output before input, and that's all you got to know. What it's doing is it's scrambling the phases of the Fourier components and phase modulating and re-scrambling the phases. So it's reconstructing an image. I mean, after all, you have an object in front of a lens, it gets inverted, okay? So this is the simple temporal analog of inversion, and it's time reversal. Okay, so now I want to just give you a short history on the whole subject of space-time duality as far as I know it. There's a lot of people in the optics community that have very strange ideas about who invented what. And this, I'm going to give you the best story I have and then try to get on with the talk. The idea of chirping pulses on a long time scale so that they could go into amplifiers and not be peak power saturated was invented by Sidney Darlington at Bell Telephone Labs. In 1947, he proposed this. He got a patent on it, as you see, in 1954. And if you look carefully at the patent, here are long, linearly chirped pulses. You pass them through a dispersive network, and they get formed up into short pulses of much higher peak power. Now, in 1951, an extraordinary man named Bernard Oliver, a polymath, brilliant fellow, was working at Bell Labs. Bell Labs had an under wraps program in Chirp radar for the military, and they couldn't talk about it for many years. But in an internal Bell Labs memorandum, he titled the memorandum "Not with a Bang, but a Chirp." And this comes from a T.S. Eliot poem, "We are the hollow men, we are the stuffed men, leaning together. This is the way the world ends, not with a bang, but a whimper." Barney, being a very well-read man and a hell of a scientist, put out this notion, not with a bang, but a chirp, and he coined the phrase chirp radar. And if anybody out there knows where I can get a copy of this memorandum, I want it because I have a book project I'm working on. And I also used to work for the man many, many years ago when I was at Hewlett-Packard. He was very intimidating, which is wonderful. I like people that are that way because he doesn't suffer fools gladly. You learn a lot if you listen. Bell Labs took the wraps off of chirp radar in 1960 and published this very famous article in Bell Labs Technical Journal, Bell System Technical Journal, which most of the people in my generation who were learning about chirped optical pulses dug this up and read it. It's still excellent, and Sid Darlington, of course, is on there. And one of my former advisors knew all these people at Bell Labs. And if you look at all the pictures, they all show, you know, linearly frequency swept or chirped pulses and pulse compression and stuff like that. But then along comes the optics community after chirp radar. And there's this famous guy named Pierre Tournois, quite a character. And if you look back in the literature, he was writing about these ideas of space-time analogies back in the 1960s, okay? So here are two papers in French, of course, which is why I didn't see them until he wrote me a letter from France and said, what is wrong with you? Do you not read French? No, Pierre, I'm sorry, I don't. Space-time correlations, this is dated, what, 1966, I think, I can't see it so well. And anyway, if you translate these and look at them, he's got it going on here. He's figured out the optical analogs for electronic configurations forming temporal images. He's using temporal images in 1966. And you see, this is all done with electronics, by the way, because he's working for a signal processing outfit. And you can see dispersion, mixing with a chirped pump, more dispersion. So he was onto it. Probably the most famous paper for pulse compression aficionados in the 1970s was Brian Tracy's paper, where he showed how you could take outputs from lasers that had a lot of bandwidth, but also had crappy pulses, and lo and behold, he could compress them from neodymium glass lasers. He says right here that identical to the formula for calculating Fresnel diffraction pattern of a slit with aperture illumination A, e to the psi. So all of this stuff went on. And then by 1968, it's in a textbook, okay? So if anybody tells you that, oh yeah, chirped optics and stuff was all done in the 70s or 80s, it's baloney. It was done long before that. So this is a book by Papoulis, a very famous author who wrote about a great book on probability if you're a mathematician. But I also dug up this guy, William Caputi, who wrote a paper called Stretch, a time transformation technique. And this was published in 1971, and he talked about space-time analogies and how to magnify and demagnify electronic waveforms using exactly the same principles, not optics. Then I dug a little deeper and found out that he was granted a patent in 1966. It was filed in 1962, so he was on it back then too. And you can see that here's an input waveform, there's an output waveform. They have the same envelope profile. Okay, but this one's bigger than that one. And input dispersion, output dispersion, mixing with a swept frequency generator, which imparts that linear frequency sweep that we need. Okay, on to quantum mechanics. So, Professor Kolner, how do we get chirps on wave functions? This is the famous paper by Yakir Aharonov. Leo, is it Aharonov or Aharonov? Aharonov? Okay. I've heard it pronounced the other way, but that would be by an American. Yeah. So this was a very interesting paper because it says in the abstract, contrary to the conclusions of classical mechanics, there exist effects of potentials on charged particles, even in a region where all the fields and therefore the forces vanish. Heresy, you say. Well, here's the two experiments that they propose. The one on the left is called the electric Aharonov-Bohm effect. And it says because the potentials enter into the Hamiltonian, that the electron wave function or any charged particle with charge q will pick up a perturbation or a contribution to the phase that is the time integral of the scalar potential times q over h bar. And in this experiment, imagine that these are two conducting metal cylinders, and they're initially at zero potential. You launch a wave function which splits at the point A, and half of it goes through that one, half of it goes through this one. I know. And while they're in the middle, and how do you know? You turn potentials onto the tubes. You make the top one go up, the bottom one go down. There's no field inside the tube, but there's a potential there. And before they exit, you turn the potentials off. So in principle, the wave functions have seen no fields whatsoever. They've exhibited potentials, and therefore, because the sign here depends, is important, if you make an interference experiment, you should be able to detect a fringe shift in the interference of the electron wave functions. The magnetic corollary to this, the magnetic Aharonov-Bohm effect, is a path integral of the vector potential dotted into the path, and you let an electron split left and right here, and you block this with some kind of a foil so that they don't go down the middle. Imagine you have a solenoid here. In a solenoid, you have B on the inside, but B on the outside is zero. But you have a vector potential on the outside. And the electron going around this way, since the vector potential lives in circles, which I'll show you in a second, it has a positive contribution to the shift here. The electron going around the other direction has the negative contribution. And when they combine at the output, you will see a shift in the fringe pattern compared to the situation in the absence of the solenoid being turned on. This is a lovely picture from Physics Today that I swiped. So this is a solenoid here, and these green lines are lines of constant vector potential surrounding the solenoid, and the purple lines are the magnetic field. And these arrows show the path integration if you wanted to do a closed loop. But in any event, inside the solenoid, the magnetic field is a constant proportional to the current and the turns density, n per unit length. Outside, the magnetic field is zero. Inside, the vector potential is linearly proportional to r, okay? And outside, it goes like 1 over r, but it's linearly proportional to the total flux enclosed, which is inside. The flux is integral of b dot ds, and it goes like 1 over r on the outside. Well, a little while later, less than a year later, a guy named Robert Chambers in Bristol, England, did an experiment and proved that it worked. And I won't dwell on it too much, but there is an electron source here and a screen over here. There's a biprism, essentially like an optical Fresnel biprism, that splits this and redirects the electrons. There's a static electric field. These two, this is a small fiber with aluminum on it at some potential, and these are the sides, and E stands for earthed. Why? Because he's English, British anyway. And so the electrons come around here, and A is where the magnetic flux is. It has to be confined. Now the dimensions here are pretty small, okay? They're of order a few microns or so forth. So you don't sit down in 1960 and wind solenoids on that size scale. He did something extraordinarily clever. What he did is he took whiskers of iron that were 1 micron in diameter and 500 microns long. Now the whisker is magnetized, so there's a magnetization inside there. And it's also tapered, okay? So as he moves the whisker up and down, or he just puts it in the place where the magnetics or the solenoid should be, the fact that it's tapered says the flux is increasing as the thing gets bigger. And remember, the vector potential is, when you integrate it, I mean, it's proportional to the enclosed flux in a plane there. And so you can see the electron fringe patterns here are tilted, okay? So as you go down the whisker, as it gets bigger and bigger, it's enclosing more and more magnetization, more and more flux, and the fringes are tilted. And it's just a beautiful experiment. I recommend reading the paper. Now, there was a lot of controversy, as you might imagine, at the time. People said, oh, there must be stray fields that are connecting from the top of the solenoid. They don't, the magnetic field surely can't go to zero right on the outside of the solenoid. Other people argued that, well, the electron's inducing image currents in the metal line or whatever. So this wonderful physicist, Akira Tonomura, who, if you watched the talk the other day by our qubit guest, he showed a beautiful sequence of images that Tonomura took, same guy. What he did, he says, okay, let's make a superconducting shell around our magnetized toroid. So there's no magnetic field leaking out of a superconducting enclosed toroid. And then he wrapped that in copper, so there's no stray electric fields and no interaction at all. And then he made a hologram using a lens here and a reference wave, and then the beam went also through the toroid. And lo and behold, here's the fringe pattern. And in the middle of the toroid, you see an exact pi shift in the fringe patterns. I think that pretty much put to bed the notion that this is some extraneous effect, and it was just an absolutely stunning experiment. Okay, so how do we interact with a traveling vector potential? We use the same tricks that we did for interacting with the electro-optic modulator, which I just show you here, just to recall. The retardation is where the action is. It's got the sync function having to do with velocity mismatch, and it's got a peak phase retardation and all that. So we want to interact electrons with vector potentials. So you can't have waveguides in the conventional sense with an electromagnetic wave because the phase velocity is greater than the speed of light. And that's just going to wash over the electron over and over and over again. So you think about slow wave structures. So the electron can co-propagate with a vector potential part of the electromagnetic field. And so here are a number of different slow wave structures. They've been known for a long time, since the 40s when magnetrons were invented, and later klystrons and traveling wave tubes and things like that. Okay. If you have a waveguide intended for accelerating a charged particle, and let's say the particle is going to go down z, okay, there has to be a longitudinal component of the electric field. And this implies that there are longitudinal components of the vector potential and the gradient of the scalar potential. So here's the key figure. Suppose we launch a wave packet, psi here, if you like, a wave function, and it co-propagates with a cusp of A or phi or both, because if it's a harmonic function, because of the derivatives up here, that will always be near a zero crossing of the electric field, okay? And it'll be where it's locally quadratic, so you get the lens action. But the zero crossings electric field will minimize, but not eliminate, local Lorentz forces, okay? Something I need to investigate more. Okay, so let's give some math to this. Let the vector potential and scalar potential be traveling waves. And then if you use the Lorentz gauge, you can equate the peak A naught to the peak phi naught straightforwardly, and then write phi in terms of A naught, and you've eliminated one variable. They're related by the Lorentz gauge. And then, since we don't like to talk about electromagnetic waves in terms of vector potentials, right, or scalar potentials often, we always talk about the electric field in a waveguide or a coax cable. So we can relate the electric field to the peak of the vector potential just through the usual definitions up there, okay? The accumulated phase shift comes about by, once again, the integrals from the Aharonov-Bohm effect. And if you write down, it's just another one of these propagation equations, okay? So gamma is going to be the peak, or it's going to be the accumulated retardation due to the interaction with the potentials. And if you solve that integral up there, in the traveling wave reference frame, lo and behold, you have that sync function again that tells you the destruction by not having the phase velocity and group velocity match, and it also goes like a cosine, okay, which is good. Now, if you substitute for the peak vector potential up here, A naught, in terms of the electric field, here you get the final expression, okay? So this is the accumulated phase retardation due to we haven't specified exactly how they got there, but anyway, some traveling wave vector A and scalar phi. Okay, In an ideal situation where the phase velocity and the group velocities are matched to each other, this term out in front disappears, and you have a simpler expression, and you can define a peak phase retardation as the product of these terms divided by the photon energy of the modulating field. Okay? The key point, though, is the wave packet, if it's confined to a cusp, then you can expand the cosine to second order, and this is the quadratic phase that's necessary for lens action. All right? So what is the focal length of a matter wave lens? Let's assume we're going to trust that this all works and the quadratic phase does what it's supposed to do. In space, we always wrote that the phase induced by a space lens can be written in terms of a focal length. Let's do the same thing for the matter wave lens, and we did this earlier for the time lens as well. We just wrote it that way and then solved for what that matter wave focal length should be. And by comparing the coefficients on psi squared here with the Taylor series expansion, you come up with this expression, okay? Which we can look at. Let's see, do I do an analysis interpretation? Nope. So this is the focal length. Notice that it is proportional to the modulating electromagnetic field wavelength squared, which says that the shorter the wavelength, the shorter your focal length. This is good. It's also proportional to how strong the peak gamma naught is, the peak amount of acquired phase shift. Okay, so what about the F number? Well, the effective aperture, as you know, for all optical imaging systems, can be defined as that region for which the phase is predominantly quadratic. So you want to have it second order. And a reasonable approximation to any sinusoid is if you cut it down to 1/2 pi, it's mostly quadratic. The next order term is just a few percent. You know, the fourth order term is pretty small. So we're going to define a window as being the modulating field divided by 2 pi. If you do that and define the F number as the focal length divided by that apparent window, you get this very simple expression here. And if we equate the classical to the quantum mechanical momentum and we substitute gamma in terms of E, we get this expression where we're going to, for the moment, assume perfect velocity matching and write the product of V squared as C squared over N squared, which N is a slowing factor. It's how much the waveguide has slowed it down, because it has to be slowing. How do we interpret that? Well, MC squared's in the numerator. That is the rest mass energy. The denominator, N is just a number, but Q E naught L is a kinetic energy of a particle if it had accelerated from rest through a distance L. I don't know if this has any meaning, but it's what it is, except the field is in phase quadrature, and in fact, it's 0 right in the middle. But nonetheless, that you can interpret it that way. Maybe you could call it a potential energy. Anyway, if you put in some numbers, if you assume an electron is propagating in a slow wave structure with perfect velocity matching, you calculate a not an unreasonable number of an F number of 5, which is pretty impressive, for not outrageous electric fields. Okay, so now you can add the space or matter wave lens column and everything lines up just rather beautifully. Okay, how do you do imaging? Well, remember, this is how we do spatial imaging. This is how you do temporal imaging. You have solution to the free particle Schrödinger equation, which is our input dispersion. You multiply it by the lens transformation, which is our matter wave lens. You follow it with output dispersion. Okay, Fourier space, real space, Fourier space. And if you concatenate all of these, okay, which is a page worth of math, you get this final result, which is writing the fields in real space in terms of an inverse Fourier transform of whatever your initial envelope spectrum was, times a quadratic phase, see, k squared, and there's your Fourier transform kernel with some scale factors. And I've taken out these constants just to make it read prettier. Okay. So the next question is, all right, that's your output. What constitutes an image? Well, we take another page out of Joe Goodman's book on Fourier optics, and we note that if you can make this quadratic phase term disappear, then this is nothing more than the inverse Fourier transform of your initial spectrum with a rescaled time coordinate. or space coordinate, sorry, space coordinate. So we just set this equal to 0, and what that says is this very simple expression, and if you fill in the ABCs and Ds, lo and behold, you get something that looks pretty familiar from regular optics, right? And in fact, it'll look more familiar if you do another substitution. There it is. But you do another substitution and you fill in for the other terms here, tau 1 having to do with the distance of propagation. That's the propagation time, propagation distance. That's the imaging condition. So it pops up and it looks exactly like it does for space. And the scale factor in the Fourier transform kernel, when you put in all of those, lo and behold, that ratio, the L2 to L1, the output to the image distance, becomes a magnification. So the output wave function is proportional to the input wave function at tau equals 0 divided by a space scaling factor m. And since m is negative, the output wave function envelope will be a scaled replica of the input, and it'll be time reversed. And you ask, well, what kind of resolution does it have? Well, if we take a page from normal optics, okay, you know that the impulse response is always going to be given by the Fourier transform of the aperture. So to a good approximation, the resolution, just like it is with a telescope or microscope, the resolution in real space in the traveling wave frame is roughly equal to the wavelength, the de Broglie wavelength, times the F number of the matter wave lengths. I'm just about running out of time here. So what we want is short modulation wavelengths. We want strong modulation. We want long interaction lengths and low kinetic energies. Can we achieve it using optical wavelengths to drive it? Maybe, but the challenge is how to make an optical slow wave structure. So just if I may take 2 or 3 more minutes to tell a good story. I was having coffee at the Ginston lab at Stanford one lovely Friday morning at the social hour, and I asked Bob Beyer what he was working on these days. And he told me about this wonderful thing called a dielectric laser accelerator. And they're basically shrinking linacs from tens of meters down to the size of your thumbnail and hitting it with laser pulses. And so here's one of the first proposal papers. And it works by sending a plane wave into a channel here. An electron beam interacts with the E field, which is polarized in the direction of the beam. So it gets a kick, except it slips out of phase with time. So you put in a phase delay, and that's what these grating blobs here, and that retimes the optical field as it comes in. And so here's some pictures that show how all this works. But to kind of jump to the end, this is a 2-stage and this is a 4-stage one. So one way you can think of it is if you look at a space-time diagram, and it takes, I guess, a second to load this. This is with no phase reversal. The electron, this is time, this is space. The electron's going to see positive, negative field, positive, negative field. There's going to be no net effect. But if you stagger it and you phase delay it on alternating sections, the electron's going to see positive here, at least half cycles. You can take this to 4 and the electron's going to see mostly positive. Well, this is a bit fanciful because the pictures, you can clearly see discontinuities in the electric field, and that's a no good. So what happened with the Beyer group is they built structures like that and they didn't perform very well. So what they did is they got this marvelous young faculty member, Jelena Vukovic, on board. She does inverse E&M design problems. And she said, let's start with the desire to have this phase matched and then figure out what dielectric structure will solve this problem. And it's an iterative kind of a problem. And there is a picture of the dielectric structure with predicted fields in it. And it doesn't look anything like those, rectangular square things that we saw before. And this has been pretty successful. This is some data from their work. And this is how they synchronize the optical pulse, which lights up an electron photoemission gun here, and that gets synchronized with the pulse that's actually hitting the dielectric laser accelerator. And there's a bunch of other really cool stuff that they've done. So let me just conclude and say that paraxial diffraction, narrowband dispersion, and the Schrödinger equation, they're all of the same form, and we want to be able to capitalize on that. The solutions are always in terms of quadratic phase filtering in the Fourier domain. If you do quadratic phase modulation in the real space, coordinates, that'll always act as a lens. So you either have space lens, time lens, or maybe quantum mechanical potential based on quantum mechanical lenses based on potentials. If you combine dispersion and a lens with appropriate and more dispersion and appropriate measure, you create an imaging system. And since all imaging systems profit from faster lenses, if we want to do it for matter waves, it looks like the dielectric accelerator is just what the doctor ordered. And perhaps new and exciting applications will come up. So what do I have yet to do? An awful lot. Careful analysis of, I know some of you are thinking about these things already, in analyzing what happens to the electrons in terms of diffraction or dispersion as it propagates through the lens. I didn't treat those together. I didn't treat it at all through the lens. The assumption is essentially is a thin lens approximation. As a wave propagates through the lens, you ignore the fact that it might diffract a little bit. I need to look closely at that. I think about shutter ideas. I didn't get to talk about what they do at Stanford, but based on streaking fields, you can probably do this and combine apertures and then do the same thing to output time resolve. We're going to need to resolve sub-femtosecond kind of timing to see these effects. And you can think about multi-element imaging structures, microscopes, telescopes, who knows? And it might be fun to do interference experiments to see if you can see the quadratic phase of the electron wave function. You can do this with static electrons, okay? But if you've got them all hitting and making at random times because of the uncertainty principle, if the phases are structured, you might be able to see interference patterns. And the big question is, do any of these ideas violate any fundamental physical laws or principles? And I'd be delighted if any of you can argue with me that they do, and then I can stop working on this. Finally, I'd like to thank the many sponsors I've had over the years on this particular branch of my career. And now I'm going to add JILA to it for this wonderful opportunity. So thank you very much for your time, everybody.
If there's any questions, I can come around with the microphone so people on Zoom can hear. And if there's any questions from Zoom, put it in the chat and I'll repeat it for the speaker.
Too much math, drain you? Good.
So is the name of the game pretty much that your phase is proportional, is equal to h bar times the action? And in order to get lensing, you have different interaction terms in the action. You're trying to find analogies for, say, like an electronic system.
Yes.
Okay.
Yes,
Okay.
I believe it is. I think that's a concise way of saying it. Yeah.
Okay. Okay. It's pretty cool. It's very cool. Thank you.
Mm-hmm.
Excellent talk. So I was wondering, right now people are studying like non-separable electromagnetic wave or inseparable electromagnetic.
Excuse me, could you repeat that?
Yes, non-separable wave solution. Basically, you have the spatial and temporal part coupled together.
Right.
So I was wondering, is there any of this framework can treat that kind of
Oh, so
wave?
you're saying do everything at once, the spatial and the temporal.
Right. the
I
spatial temporal.
haven't done that. That's very complicated. And at the very outset, when I said, here's the diffraction problem, here's the dispersion problem, I completely separated them, as you saw, because you can wrap your head around it analytically and understand the fundamental features. Certainly you could do them together, and you could certainly hand it to a computer because they don't sweat and they don't cost anything once you bought them. But I have not done it, but it's an interesting question.
All right, 1 second.
So Brian, part of the spatial imaging charged particle is this. You're using electrons. Try to do when you talk about matter wave. The ultimate goal is really using electron imaging.
Sure, why not? But at least the way the equations are written,
Yeah.
the interaction comes through with charged particles because there's a Q in front of that delta phi.
Mm-hmm.
But people have been studying this for neutral particles as well. Not what I'm talking about here, but they've been looking at the Aharonov-Bohm effect for neutral particles and molecules as well.
Okay.
Yeah. And I can't remember exactly how that works because it's in a stack of papers still.
The other thing which I didn't know in my ignorance, but maybe you can comment on it since you went through the history of the chirp pulse amplification. And of course, we all know,
Yes.
in 2018, the Nobel Prize went to the two optics pioneers, Gerard Monroe and Donna Strickland, for
Yes.
their invention of optical chirp pulse amplification.
Yes.
You made some comments, but you did not make the explicit. Are they connected or?
They're absolutely a one-to-one copy, if I may, of chirped radar transmitters.
That's what you're implying. Yeah,
Yeah.
that's what.
It's the same idea. I mean, it was a brilliant idea. I don't want to take anything away from Gerard. I've known him since I was a graduate student. But it is moving from what was invented in the microwave domain and applying it to optics. Not the first time it's happened. Do you know the origin of mode locking, for example?
Nope.
In 1956, Chapin Cutler at Bell Labs took a traveling wave tube, the output in a waveguide, and put it through an expander. What is an expander? It's what we call a saturable absorber.
Yes. Mm-hmm.
And then took the output of the expander back to the input of the traveling wave tube.
So you have a
Passive mode
nonlinearity and a feedback, and you got a mode locking.
He saw ultra short electrical pulses in the
Yeah.
microwave domain with about 30% fractional bandwidth. We call that mode locking nowadays. And he did it first in the microwave regime. So I suspect guys like Tony Siegman, who was quite cognizant of the work at Bell Labs in the 1950s, and other people were thinking about how to do that with lasers. He was one of the pioneers in doing analysis of mode locking. So yeah, this stuff comes around. I mean, I thought I had some original ideas in this. No, in the time lenses and stuff like that, I was rather delighted to find out that there was prior work. But as is often said, 6 months in the lab will save you 2 hours in the library.
Thank you.
Yeah.
I don't see any questions online, but I do see Jan has turned on his camera. So hi, Jan.
Hi, Jan.
We've actually lost your video earlier, unfortunately, but I can
Okay.
get you to start video. There you go.
This is absolutely fantastic stuff. I can remember as a visitor in Stanford one time in the 80s.
Yeah.
Ted and I were talking about making the waves as smooth as possible.
Mhm.
And the crazy other guy was talking about pulses and curvature. I enjoyed those interactions enormously, Brian.
And now you've seen them come together after all these years.
Indeed, it's totally wonderful.
Yep.
That realization that you burn out microwave tubes, and so stretching the pulses out is an easy way to see how they might have been thinking of that. And I guess maybe doesn't burn the tube out, but rather makes a spark, and that limits.
It does all of the above. And I think that was the whole point. If you read Darlington's patent, it's in about the 4th paragraph.
I didn't know about that before, so I thought that our optical community had invented it from that motivation, but it's the usual thing. There's been smart guys before.
Yeah. If you want,
Propose that we thank the speaker once again, just so we can release the audience.
we're going to release the kids back to the lab.
Yeah, go back to work.
Thank you.